how to trace an algorithm that has recursions or recursive functions. Recursion is a programming technique that allows us to reuse a function by the function itself. That means a function will call itself automatically, and that will create an endless loop, because if the function calls itself, so the process will go on forever. So that's the reason why we all know that recursive functions has two cases. Case 1 is the base case, so that's the stopper, and the other one is the recursive case. That means recursive case is the default case, so by default the function will keep on calling itself, and base case will work as a stopper that will stop the process, stop the loop that will be created due to recursive function. If we look at this algorithm, the one we are going to trace, the function fib, the base case here is if the number is less than or equal 1. So if you look closely, only this one does not allow to call the function again, rather it has a independent statement. But if this condition doesn't match, on the else case, we see that the statement features the functions. That means it calls the function again. So we can say the else case in this conditional statement is the recursive case. And there is another base case. So interestingly, we have two base cases here, because at one point, if we go out of this loop, out of this conditional statement, we find another return statement that also returns the value, or that also does a certain operation, not calling the function itself. All right, now if we start tracing the function, we can see that it has call number, function call, number 5, result, and return value as seen on the label of the table. And we are going to trace the table with this fib5. All right, that means the first function call is call number 1 fib5. Basically, this algorithm is giving us a Fibonacci series created automatically by setting an ending point. It tracks back and gives us the series values. All right, so number 5, and what's the result? So if we start doing it, function fib number, it has a parameter here, integer type of parameter, it returns integer. Okay, nice. If number is less than or equal 1, so our number is 5, which is not less than or equal 1. That means we go to the else case, which is a recursive case. Result fib number minus 1 plus number minus 2. That means the result of this step is fib number minus 1. So number was 5 minus 1 is 4, plus fib number minus 2, 5 minus 2 is 3. And there is no return value, because the recursive case is calling the function again, that is taking us to the beginning of the function again, not to this statement. So we could not reach the final statement, rather we are in a loop of recursion. So we don't have any return value, rather the result is giving us two more functions to call. So more functions call means we need to log them. So call number 2 is fib4, and of course the number is 4. And if we call this function fib, number is 4, so we have to compare this. Is 4 less than or equal 1? No. That means we again go to the else case, which is again a recursive case. Interesting. So fib number minus 1, which is 4 minus 1, 3, plus fib number minus 2, which is 4 minus 2, that is 2, and no return value once again. And we have the other one here, fib 3, right? So call number 3 is fib 3, number is 3, so let's make the process faster. Fib 3 minus 1 is 2, plus fib 2 minus 2, 3 minus 2 is 1. And 1 is a base case, by the way. So but we still have fib 2, so let's do this first. Call number 4, fib 2 gives the number 2, and fib, again since 2 is less than or equal 1, that means it will not go here, rather it will come here, where again the function is calling itself with the statement. It is calling the function twice, so that gives me fib number minus 1, which is 2 minus 1, fib 1 plus fib 0. So we have touched the base case. Basically the idea is to go on, call the function again and again till we reach the base cases like this, so that we can compound and we can come back to collect all those return value, because the other steps they could not produce any return value, as the function was being called again and again, not allowing us to go to this statement, the last statement, where we could have a valid result. But now that we have reached the base case, now we can start collecting the numbers. So call number 5 is now fib 1, and fib 1 will finally make this statement true. I'm talking about this statement. Let me collect a different color. So fib 1 will make this statement true, which is a base case that gives result a certain value, which is 1. So number is 1 and result is 1, because this statement is giving us 1. Now 1 itself will be the return value. Why? Because after executing this statement we come here and we bypass the else one, right? Because if the condition is true, we don't go to the else and we break through and we go outside of the condition statement and we get return result. Remember what is our result? It is in the trace table, so the value itself is the return value. Nice. Then call number 6 is fib 0. Now we started compounding. Look, fib 0. So fib 0, number is 0. 0 is again, I will highlight again makes this statement true. I'm talking about this one. So if this statement is true, result is the number itself. Look, number is going to the variable result. So number is 0. 0 is the result and return value is also 0. Now as we have touched the base cases like this, and we now have solid values. Now we can recalculate and send them back to the previous steps where we left with no return value. Look, these are the groups where we ended up calling those functions but not having a result, concrete result. Now that we have touched the base case, now we start sending them back to the previous recursive cases so that the values are collected and added together. How? After number 6, now let's start compounding from here. Step 4 features fib 2, which is fib 1 plus fib 0. So we take 4, and since it's a repeat, let's use a bracket. It's fib 2 that originally had the number 2 that originally had fib 1 plus fib 0, and back then we did not have the result to fill the return value because we did not know the result of fib 1 and fib 0. Now that for fib 1 and fib 0 we have 1 and 0, we can return those numbers, right? Now that we know fib 1 is 1 and fib 0 is 0, so we can easily add them together in result 1 plus 0. And why 1 plus 0? Because fib 1 is 1 plus fib 0 is 0, so result is 1. Then we do number 3 where fib 2 plus fib 1, so fib 3 number is 3, fib 2 plus fib 1. Interestingly, now fib 2 has a solid result, right? So fib 2 plus fib 1 also has a result. Fib 1 is 1, so 1 plus 1 is 2. Number 2, fib 4 has fib 3 and fib 2, which is fib 3 is, look, now I have the result of fib 3. Fib 3 is 2, so I can replace fib 3 with 2 plus fib 2 is here fib 2 1, so 2 plus 1 is 3. And finally we do first step where fib 5, the first call that did not have the values to fill, but thankfully now we have. Fib 5 is fib 4 plus fib 3. Fib 4 is 3 plus fib 3 is 2, so 3 plus 2 is 5. Alright, so this is how we trace an algorithm that has recursive functions. What happened? Quick recap. From the first one, initial call, we had the recursive functions calling itself, didn't have the value. Why? Because it was a journey that started, that went from, let's write here, from 5 to 4 to 3 to 2 to 1, and 1 has a result value that will be returned, passed on to the previous steps. Now the 2 also has a result, it gives back to 3 gets the result, gives back to 4, and finally we get the result. And from this we create the series 0 1 2 3 5. That's the Fibonacci series of 5 elements. So I hope you understood. This is how we can trace any algorithm that has a recursive functions. We start calling the functions until we reach the base case, and base case will give us a result. Once we get a result or value, then we have something to work on. We reuse them and collect all the results like this. I hope you understood. If not, we can again have a different algorithm to trace recursive functions. Till then, take care everyone. I'll see you again.